This is section 5.6. It's substitution, often called u-sub. So here's the deal. We've been finding antiderivatives, but we have a problem now. If you look at this, we did trial and error in the previous sections trying to figure out what to do. Now, we have a power rule. If I have x cubed, that's easy. I just add 1 to the exponent and divide by that. And that'd be easy to do. But here's the problem now with what we have here. We have 2x plus 1 to the third power. Now that's an issue because we don't know how to do that. I mean, we could trial and error and try to figure out what's going to work. But we wish this here were a single variable. So this is going to be the backwards of chain rule, where we had box. Basically, we're going to have box again. So the box is going to be what we do our substitution with. So we're going to say, hey, I wish this were a single variable. How can I get a single variable? I'm going to redefine a new variable. I'm going to say let u equal 2x plus 1. And that's kind of cool now because when we rewrite this, we're going to get this, 2u cubed dx. We have a few issues here. So this we could say, hey, I add 1 to the 3 and divide by that. But the problem is this dx is telling us our variable is x, not u. So somehow I got to get this to be a du. And so that's what I need to figure out. How do I convert that to a du? There's going to be two different ways to do that. So I'm going to show you both ways. Well, to get a du, it's going to be involved with this new statement we have. So I'm going to take the derivative. That will be du dx is 2, because the derivative of that is 2 and the derivative of that is 0. And I'm going to move the dx to the other side. Now this is the first method. Then you said, you know what? I want a du. I don't want a dx because I changed my variable to a u. But I need a 2 dx to get that. But lo and behold, check this out. You have a 2 dx. So all that's going to change into du. And so now the equivalent is u cubed du. So all we did by changing our definition, we defined a new variable u, and doing things that we're allowed to do, take the derivative, rewriting it du, and we notice right here that is equivalent to du, so we replace it with the du. Now we are able to integrate. We add 1 to the exponent, divide by that, plus c, and then we replace u with what u is, 2x plus 1. So our final answer is going to be 2x plus 1 to the 4th over 4 plus c. That's our antiderivative using u-sub. That's technique number 1. Let me show you the alternate technique that some of you might like better. So let me erase all this. Now at this point, I want to get rid of dx. I don't want any more because my variable is u. So if I solve for dx, divide both sides by 2, dx will be du over 2. So I can place du over 2 in for dx. I get 2u cubed, and I replace it with du over 2. Those 2's cancel, and everything else is going to happen the same as the last problem. I use the power rule. I add 1 to the exponent and divide by that, plus c. And I replace u with what it is, 2x plus 1 to the 4th over 4 plus c. So those are two methods for replacing dx with du. And whatever you prefer, you can do. All right, for our next example, what is it that we do not like? I wish that this were an x. Because if this were an x, I am my own grandpa, so the antiderivative would just be e to the x. But no such luck. This is box. And so I wish that were a single variable. So I'm going to say, hey, I'm going to define u to be that 10x. And the great thing that does for us is it becomes e to the u, which I like, but we have the issue again with the dx. I don't want a dx, I want a du. So du dx would be 10, so du would be 10 dx. And fortunately, look at that. That is equivalent to du. So I'm going to replace that with du. So I have e to the u, and the red part becomes du. The antiderivative e to the u, I am my own grandpa. But I replace u with this equivalent 10x. So it's e to the 10x plus c. Dun, dun, dun. There's my answer. Now the other method I will do for you. Let me erase all this. So the other way is to solve for dx. So I divide both sides by 10. I get du over 10. And I place this in lieu of dx. So that will get me 10 e to the u, and I replace dx with du over 10. Fortunately, those 10s cancel. I get e to the u du. I am my own grandpa forwards and backwards, and I replace u with 10x. And there's my answer. So for the rest of the way, I will change methods whether I do the first method or the second method, because I don't want to do two methods on every problem. So for this one here, this is clearly the function inside of another function which I want to replace. Because if that were a single variable, that would be awesome, right? So what we're going to do here is let u be that. Now if I do that nicely, this becomes x to the 4th, u to the 9th, dx. I still have two problems now. That and the x here. I want everything to be u's. I don't want any x's. Well, let's find du. Du will be 5x to the 4th dx. And so we look and we say, you know what? I want 5x to the 4th dx. And I almost have it. If we look here, and I say to myself, I wish there were a 5 in front here. Okay? But you're allowed to multiply by 1. So I'm going to put a 6, actually a 5, sorry. A 5 there and a 1/5 in front. So what just happened? That's equal to 1, 1/5 and 5. So I didn't change anything, but now I have my 5 that I wanted. And so now I have 1/5. The part in red is all replaced with du. So I have 1/5. I use a power rule. It's u to the 10th over 10 plus c. And now I replace u with x to the 5th plus 6. Whoa, that's not right. Plus 6. That's all to the 10th power. And on the bottom I have 50 plus c. So that will be example number 3. Let's keep going. Example 4. So where's my function in my function? Let me rewrite this. This is cos x cubed times sine x dx. And it appears there's my function in the function. It's not always this easy. Sometimes you have to experiment and try different things. But it works out nicely in this case. So I wish this were just a single variable. Then I can use the power rule. So I'm going to let u equal that cos x. That's going to make du minus sine x dx. Do I have that? I don't quite. So I'm going to use the other technique where I solve for dx. Dx, divide both sides by minus sine x. And here's what I'm going to do. I'm going to take this and put it in for dx. So I still have, back up a little bit. And I'm going to replace cos x with u. So I'm going to do that both at once. So I'm going to get u cubed. I'm going to have a sine x, and dx gets replaced with that. So that's going to be a du over minus sine x. And nicely, those signs cancel. And what am I left with? Let me box this up so I don't confuse it with, it's side work. So what I end up with is u cubed du. That minus, I'm going to pull out in front and move it here. I'm going to use my power rule, add 1 to the exponent, divide by that, plus c, and replace u with cosine x, which I can also write like this. You need to be comfortable with both ways. And so there is example number 4. So you just got to try picking a u. Now, if you would have did, hey, let's try u be sine x, you can run through that and you're going to realize it's not going to work. Most times it's going to be the function inside of another function, but not always. So I just want to say that. And so there's a point where you have to start seeing some shortcuts and some secrets, and that only happens with practice and experience. Okay, so here we go. What do we do with number 5? So hopefully you're seeing that this x plus 1 seems to be what our u should be. So we're going to let u equal that x plus 1. And what are we going to get? X over square root of u. And now that dx, let's take the derivative, du is going to be 1 dx. So therefore, I can replace dx with du, and I will do that. And we're so close, but we have a problem. Hopefully you see it. Now my variable should be u, and I have an extra x there. So when you have a leftover x, or x squared, sometimes you can replace it using your statement here. I'm going to take that statement, u equals x plus 1. I'm going to solve for x, subtract 1 from both sides, and now you have kind of a cool substitution. You can replace x with u minus 1. Let me get rid of this stuff over here. Now, you might be saying, how the heck would I know to do that? So that is something that is just you experience. You see that, hey, I have an extra x. Can't I take my statement and replace it? Solve for x and use that for x, and now I have only u's. So sometimes it works, sometimes it doesn't. You just kind of try it and see if it works. So that you try when there's extra x's left over. Now I'm going to rewrite this as 2 separate fractions. And then there's a power of 1 that you don't see there. And the rule is you subtract the exponents, so 1 minus 1/2, and u to the negative 1/2. So if I have an exponent on the bottom, I can move it to the top and change that sign to negative. So I'm almost done here. So this will be u to the 1/2 plus u to the negative 1/2 du. And the rule is I add 1 to the exponent. So it's u to the 3/2 divided by 3/2 plus, and I add 1 to the exponent, so it's going to be 1/2, but I divide by that, plus c, and my final answer, I multiply by the reciprocal of that, so I get 2u to the 3/2 over 3, plus, and again, multiply by the reciprocal, 2u to the 1/2 plus c. And now, for the final thing, I replace u with x plus 1. I'll get my final answer. 2x plus 1 to the 3/2 over 3 plus 2x plus 1 to the 1/2 plus c. And then just rewriting it, I can use the square root and cube that, and I'll explain that again. Square root. So what just happened? And I might actually do this another way, because you might see it in factored form. But that 2 on the bottom means square root. The 3 on top means cubed. And this means square root. But let me do this another way. I'm going to factor this. So they both have a 2, and they both have an x plus 1. So I'm going to take those out. But they also both have a 3. And you're saying, I don't see a 3. Well, I'm going to multiply by 1, 3 over 3. Now you see the 3. So I'm going to take out a 2/3 and x plus 1. And I always take out the lowest power, which will be a 1/2. And what's going to be left over? Well, the 2 and a 3 I took out. And I took out a 1/2 from there. What's left? Well, we've done this before. That plus that must equal 3/2. So it's got to be 1. Because when you distribute and multiply, when you multiply exponents same base, you add those. 1 plus 1/2 is 3/2. Plus, I took out 2/3, so I still have a 3 left over there. And that's all gone. So all I'm left with is a 3. And then magical things happen. X plus 1 to the 1/2. And this is going to be x plus 4 plus c. Kind of cool. 2 square root of x plus 1, x plus 4, all over 3 plus c. That's just another form of an answer, just doing some algebra stuff. But that will be example 5. Looks kind of crazy, but most of that was algebra. The calculus part wasn't too bad. I'm going to erase all this. And keep going. Example 6. So this is a tricky one. You know, it's like, what the derivative of what is tangent? We don't know. But we can rewrite this. And this is just a technique that you just experiment and try. You just rewrite it. We know tangent is sine over cosine of x. Now, this one's harder because you don't see what u should be right away. Should u be sine or should u be cosine? But here's the deal. This is going to stem from this. The integral of 1 over x dx is going to be ln absolute x plus c. So that's the form we're shooting for. Now this is through experience. You start to realize this. Trial and error. So we're going to make the bottom one our u to get our 1 over u. So let's let u be cos x. So what we're going to get now is the cos x on the bottom becomes a u. But we have a problem because we don't want dx. We want to change everything into u's. So let's do this. Du, the derivative cosine is minus sine x dx. Now, this could almost change right away to du. The only difference is minus. So technically, I mean, if you see it, it's just minus du. But we're going to do the other method. So we're going to solve for dx, divide both sides by minus sine x, so du over minus sine x. So we get to replace dx with that, and here's what we're going to get. Sine x over u, and that's going to be du over minus sine x. And those cancel, and here's what we're going to do. We're going to pull the negative out in front. We get du over u, but that's just ln, absolute value of u, plus c. And we replace u with cos x, because u is cos x. Cos x plus c. So now we have found the antiderivative of tangent x by doing a u-sub. All right, we have 3 more examples to go. Now what's different here? We have definite integral. We have to use fundamental theorem of calculus here. So not just find the antiderivative, but we're going to find the net area. So we're going to go through the same process. To me, it looks pretty clear that that's going to be our u. So we're going to let u equal that. And then let's find du. That's just going to be 1 dx. So this one actually works out nicely because that dx is equal to du, and that x plus 3 is equal to u. So I can just plug that in, du on top and u cubed on the bottom. But here is the important part that you have to not make this mistake. It's a common mistake people make. This tells us our variable's x. What that means then is the bottom variable is x equals 0. The top variable is x equals 2. Those are x's. So the mistake people make is they put a 0 and 2 here. That would imply that u is 0 and u is 2 because our new variable is u. But no, these are x's. So you cannot put x's there. You got to put u's there. So you need to use your equation, u equals x plus 3, and find out what happens when x is 0. When x is 0, u equals 0 plus 3, u equals 3. So that's your first set of values. Then you make x equal the top number 2. So when x equals 2, u is 2 plus 3, u is 5. So the 0 becomes 3 and the 2 becomes 5 because you're replacing these x's now with u's. So on the bottom it's going to be 3 and the top is going to be 5. And again, that's because u equals that. Now, you don't literally write those u's and those x's. I'm just showing you that your variables have to match. If that's an x, those are x's. If that's a u's, those are u's. Okay, here's the next mistake people make, but let me just keep going here. So let me rewrite this because I can't use the power rule. So I'm going to make the u, move the u on top. Now I just use the power rule. So the power rule says I add 1 to the top, so that's going to be negative 2, divide by that, and the fundamental theorem says I plug in 3 and 5. So here is the mistake people make. People will replace u with x plus 3. Now okay, let me keep going here. Let me rewrite this. This will be negative 1 over 2u squared from 3 to 5. So this moves to the bottom because the negative exponent, and I just move the negative in front there. So here's what people will do. They'll change that u back to an x. And here's why that doesn't make sense. Don't do this. I'm just showing you. If I replace u with x plus 3, because u is x plus 3, if I were to do that, These are what? X's or U's? Those are U's, right? I found U values. So you can't plug these in and use the fundamental theorem because these are X's and these are U's. So the crazy thing is, why did you go back to the X? You had U's already. These are U's. You don't have to go back to the X. So the moral to the story, and I'll explain it. When everything has been replaced, the X's have been replaced, don't go back when you have a definite integral because those are U's and those are U's. You don't need to do that, okay? You can, but if you do, you have to change that back to X's and those back to X's. That's extra work. You don't want to do that. So here's the example. So you are dating someone and you have issues. And so you break up. You get rid of the X. You get rid of the X's. The X's are all gone. Life is so much better, less drama, less issues, and everything is working out nicely. Why would you go back to the X? Don't go back to the X. It'll cause problems. You think it might be better this time. They're going to change. Things are going to get better. It doesn't happen. 99 times out of 100, it doesn't happen. Don't believe the lie. Don't go back to the X. Stick with you. You're better off with you. All right? So let's use the fundamental theorem. I replace u with 5. Then I replace u with with 3. And the fundamental theorem says I subtract those. So I get -1 over 50. The 2 minuses become plus, and it's 1 over 18. I'm not going to add those. I'm going to stop right there. You could get a common denominator, but that is your answer. Never go back to the X. It causes heartaches and problems. Because think about this. If somebody gave you this problem and said, solve it, you would just do this. You would never even think about going back to X's here. Because that's not even in your realm of thinking. It wasn't given to you. So why would you make that extra work for yourself? So 2 more examples. We'll keep going. All right, this one. There are multiple things you can try, but this is the ln one, where if that becomes a single variable, that will make life easier. So we're going to make u the bottom. So du is going to be 2x dx. And so here's what I'm going to do. I'm going to use the other method. I can't remember what I used last time, but I want 2x dx. And I look here, let me do a different color on that so it doesn't confuse. I want 2x dx. And I look here and I'm like, dang, I don't have it. I wish upon a star there were a 2 there. But now I have a 2 there because I multiplied by a half. So the question is, do I have a 2 there? And the answer is, now I do. Now I do. So what happens here? The half stays. All of this gets replaced with du because that's what du equals. And x squared plus 1 gets replaced with u. Bammo. That's going to be ln absolute u, right? But these are x's. So when x is 0, u is 0 squared plus 1, because that's what it says here. So we get u is 1. And then when x is 4, u is 4 squared plus 1, or u is 17. So we'll get 1 and 17 here because we replace that. All right, let's keep going. Let me box this off so I don't confuse that. So I have a 1/2. The antiderivative of 1 over u is ln absolute u from 1 to 17. So I plug in the 17 first. I don't need the absolute value because it's already positive. Minus 1/2 ln, I put a 1 there. But we all know that ln of 1 is 0, right? We all know that because the ln function looks like that, and the ln of 1 is 0. We all know that. So there's our answer, 1/2 ln of 17. And if you want to be cool, you can p in front of the log rule, move the half up there, which is ln of the square root of 17, if you want to do that. All right, one more example, and we shall be done. El dano. So let me rewrite this for y'all. So it's sine x to the 4th power cosine x dx. I'm going to let u be sine x. So that way I just get u to the 4th, which is pretty. That'll become u to the 4th. But I need to get rid of dx, right? So I'm going to solve, take the derivative. Du is cosine x dx. Well, life is beautiful because that is right there. That gets replaced with du. Sweet. It worked out nicely, did it not? I'm almost done, but these are x's. I got to convert them to u's. So when x is 0, u is sine 0, which is 0, because that's what u is. I use that u equation. When x is pi over 2, u is sine pi over 2, and we all know it's 1 because we know our unit circle. So it becomes 0 and 1 instead. Man, this is a sweet problem because it works out nicely. The antiderivative, I add 1 to the exponent, divide by that from 0 to 1. I plug in 1 first, then I plug in 0, and I subtract those, and my answer is 1/5. Done. So that is the lesson on u-sub. This lesson, it just takes practice. Make sure you're just not memorizing things, but it makes sense why you're doing what you're doing. And that's it. Bye-bye.